so in the name of Allah, the most merciful and most beneficent, let us begin our discussion from the previous weeks on pure mathematics. We have some 2 lectures on real analysis, and this is going to be the last one. And in this one, the first thing that we want to discuss is what we call the sequences of functions. Sequences of functions. So previously we have done what a sequence is and what do we mean by convergent sequences, and there are some related theorems, and we discussed what we call series as well, and what are the conditions under which the series converges. Today our topic is related to the previous topics, what we call the sequences of functions. So sequences of functions is basically a map Fn that runs from some interval to the set of real numbers. But this sequence has some parameter, or this function has some parameter n. And for all n to be in the set of natural numbers, we get a function here. It means if we change the value of n, we get a different function. So what we call this a sequence of functions. So in this one you take x and the output is going to be fn of x. So if you fix your n, let's say 1, then this becomes a function. If you fix your x, let's say I am taking x tilde, then this becomes a sequence. So fixing the value of n gives me a function, and fixing the value of x, the input, gives me a sequence. So there are so many examples for this, but mainly we are interested in the convergence of the sequences of functions. For example, we have fn of x to be 1 over n times x plus 1. We call this particular thing to be a sequence of functions. Whenever you fix the value of n, this becomes a function, and whenever you fix the value of x, this becomes a sequence. For example, I am fixing the value of n, so it will be f1 of x would be x plus 1, so this is a function. I am fixing the value of n to be 2, so this becomes 1/2 times x plus 1. I am fixing the value of n to be 3, this becomes. So these all are functions, but we call this particular thing to be a sequence of functions. Similarly, what happens if you fix the value of x? For example, I am fixing the value of x to be 2, because x is something that belongs to some interval, and interval is contained in the set of real numbers. So whatever value I can take. Let us take x is equal to 2, so this becomes 2 over n plus 1. It's a sequence. So fixing the value of x gives us a sequence, and fixing the value of n gives us a function. We are mainly interested in where does this particular sequence of functions converge. Roughly speaking, if you look at this thing, what happens is n goes to infinity fn of x. So limit n goes to infinity 1 over n times x plus 1. So if you apply the limit, we are not going into the definition that what do we mean by the convergence of this particular thing, but you can look at this limit. Limit n goes to infinity 1 over n times x plus 1. You see this term becomes 0, and we will say that the limit of this function is 1. It means we say that this sequence of functions converges to f as n goes to infinity. It means 1 over n times x plus 1 converges to 1 as n goes to infinity. This is what we call the sequence of functions fn, and this is what we call the limit of these sequences of functions. So this thing is very much interesting because we call this particular convergence to be the pointwise convergence. Pointwise convergence for the sequences of functions. It means that what you do basically, you fix the value of x. Let us say the value of x is 2. You get a sequence, you check that what is its limit. If you apply limit n goes to infinity on this one, again your answer is going to be 1. You fix the value of x to be something else. Let's say I am fixing x to be 100. So 100 over n plus 1, and if you apply the limit again, that becomes 1. So we say that fn converges to f pointwise as n goes to infinity. In mathematical terms, the definition is a bit different, but this is the idea that what we mean by the pointwise convergence of sequences of functions. We should at least know that what is the definition, so let me write that. How can we define the pointwise convergence? So we say that fn converges to f pointwise. Then what happens that difference between fn and f can be estimated by some smaller number epsilon. But when does this happen? You have to choose one x. It means for all x in your interval. It means you can choose x to be 2, x to be 3, but it should be part of your interval. For all x to be in the interval, what happens? There exists for all epsilon positive, there exists some capital N in the set of natural numbers such that this thing is less than epsilon whenever you go beyond that fixed value n. And these functions should be evaluated at your chosen x. It means you can choose any x. For all x means you can choose any x. This thing must be there, and this is what we call the definition for the pointwise convergence. It means the difference between these can be made as small as possible. Whenever n goes to infinity, or n becomes very, very large. So this is how we define the pointwise convergence. We'll come to different examples as well, and then we'll see, let's say, what happens.
Sir, यहाँ पे स्टार्टिंग में हमने fn एक फंक्शन लिया हुआ है I to R. इसमें मींस हमारी जो है इनपुट्स दो हैं, या तो हम n पुट कर सकते हैं या x पुट कर सकते हैं, और एट अ टाइम हम n1 पुट करेंगे या n को वेरी करेंगे या x को वेरी करेंगे. अगर हम n को वेरी करेंगे तो हमारे फंक्शंस बनेंगे, और x को वेरी करेंगे तो हमारे सीक्वेंसेस
बनेंगे. Right. So this is the function, and we know very well we are talking about real valued functions. So our domain is, it may be the set of whole real line, but we can take a part of it as well. And the codomain set is the set of real numbers. And in this one, my input is x, my output is fn of x. Then I can call this thing to be, it's a sequence, but it's not an ordinary sequence, it's a sequence of functions. So whenever I fix the value of n, let's say in this case I am fixing n to be 1, n to be 2, n to be 3, then I get a function.
Sequence of function.
Yes, sequence of functions. But if I am fixing the value of x, let's say x tilde or whatever, Let's say I am fixing here the value of x to be 2, then I get a sequence. So fixing the value of n gives me a sequence of functions 1, 2, 3, and fixing x gives me a sequence. Then I can talk about, okay, what is the limit of this sequence? I have taken the same example fn which I have taken there. I am finding out the limit. Here we can apply the ordinary techniques. Then this limit is going to be 1. It means I can say that this sequence of functions fn, which is that one, converges to f, which is this one, as n goes to infinity. But this convergence is called pointwise convergence. Okay, so pointwise convergence, this is the definition for that. But there is another convergence, what we call the uniform convergence, which is something very good. Because pointwise convergence is not so much strong as compared to uniform convergence, but this is what we call the definition of pointwise convergence. That the difference between your fn and f can be made as small as possible when you make your n to be very much large. And this happens for all x. For all x means you choose a particular x, then this happens. You choose another x, then this happens. You choose third x, then this happens. So this is for all. This is what we call the pointwise convergence. But this is not the good thing about convergence of the sequence of functions. We should have some other thing what we call the uniform convergence. If you see about the graph of this function, that is very much interesting. You have this function. Let us define my interval to be from 0 to 1 for now. So let's say this is 0 and this is 1. Can you tell me how can I graph this function?
It's a straight line.
It's a straight line
Will cut on
with a slope 1 and y-intercept 1. So this is 1, this is 2. So this fn, its graph will look like this. This is my, you will graph it between 0 and 1, this is the graph. What is the graph of this? Y-intercept is 1, but the slope is 1/2. So you will get something like this. You will get something like this. And for this, you will get something like this. And when you find the limit, the answer is going to be 1. So it's exactly this horizontal line. So these lines Fn, F1, F2, F3 converge to this particular function, what we call f, which is equal to 1. So graphically the things are very interesting as well. For example, if I am taking another example, let's say so the example is Fn again that runs from 0 to 1 to the set of real numbers, and it is defined as this. It is defined as n square x and 1 minus nx. How can I graph this? And this is like when x belongs to 0 to 1 over n. It's 0 when x belongs to 1 over n to 1. Can you visualize this function? Or just help me visualizing this.
Quadratic.
You fix n is equal to 1, what happens? You give me the value of f1, f1 of x. It means, first tell me what is going to be the interval. Interval is from 0 to 1. And what is this? 1 over 1 to 1. It means this becomes only a single point. So this becomes 0. And if you put n is equal to 1 here, what happens?
1 minus
X 1 minus x. And if you graph this function, what happens?
x minus x square. quadratic का
It's quadratic.
parabola type है.
Okay, I think this is not that much interesting. Tell me what is f2. You put there 2, what happens? 4x and 1 minus 2x. And this is when x belongs to 0 to 1 half. And this is when x belongs to 1 half to 1. It means, how does the graph look like? I have 1 here. From 1 half to 1, the value of my function, let's say this is 1 half, the value of my function is 0. And this is something quadratic, but it will be something like this because this coefficient is going to be negative. Similarly, when you take f3 of x, I'm not going to do the exact thing, but I'm going to tell you, take 1 over 3 here. From here to here, your function would be 0, but in this interval, it will look somehow like this. Yes. If you take like f4, it means take 1 over 4. From here to here, it's going to be 0. Then it would be something like this. So you can see that whenever we are approaching n goes to infinity, this thing will be exactly 0. But actually, near to 0, there would be a jump. There would be a jump. The height of the jump would be very much big. So this is what we call the sequence of functions. And can you tell me what is the convergence of this one? You can see that if n goes to infinity, exactly near to 0 to 1, this will be 0. This will be 0. But exactly in this short distance, there would be a jump. So I'm not interested in this jump. I can say that the sequence of this functions converges to 0, pointwise. Pointwise convergence is to 0. But you can see that if you apply n goes to infinity in this one, that explodes. This result becomes infinity. But you have to look at the limits as well. If you apply n goes to infinity, what happens? 1 over infinity becomes 0. It means this becomes only a point. On that point, your function explodes. But on the remaining points, it's going to be equal to 0. So you have to look at the functions as well as their limits. Okay, why this thing is not that much interesting? For that, I am going to give an example that we should define what we call the stronger notion, uniform convergence. So I am giving another example. Just help me draw the graph of that one. So my fn of x is one x minus 1. It is 1 when x is greater than or equal to 1 over n, and this is when x is less than minus 1 over n, and this is when x exactly belongs to minus 1 over n to plus 1 over n. Okay, what is going to be f1? f1 of x is going to be same 1x minus 1. Now I don't have any parameter n here, and lies in the set of intervals, the sub-intervals that I have so far. So if n is 1, this is x is greater than or equal to 1, this is x belongs to minus 1 to plus 1, and this is x less than minus 1. How can I graph this one? So let me draw it here. So if x is greater than or equal to 1, the value of the function is 1. It means this is 1. The value of the function is exactly 1 here. And when x is less than minus 1, this is minus 1, the value of the function is minus 1. Are you okay with this? And exactly between this interval, the value of the function is x. And you know very well x is just a line. It goes like this. Is this a graph? This belongs to minus 1.
It open up.
It is open from here. But this one is included in this one.
ठीक
So
है।
there would be no any problem.
सही
There would be no any problem. This is the graph which is a continuous function. And I think it is continuous. It is not differentiable, but it's continuous. Can you tell me what is F2? Let me write F2 here. Okay, this is done. What is F2? F2 is same 1x minus 1, but the intervals are going to be different. This is x is greater than or equal to 1 half. This is x is less than minus 1 half. And this is when x belongs to minus 1 half to plus 1 half. It means it is 1 from 1 half. So this is my 1 half, let's say. My function is 1 in this whole domain. Let's say I am denoting it with the dotted line from 1 half. And less than minus 1 half, it is minus 1. So minus 1 half, it is going to be minus 1 in this way.
vertical line है जी
Yes. Then it will look like this.
आस्ते आस्ते
Yes. You will see that when you go somehow ahead, you go somehow ahead from here, then you join these things with the third line. Can you tell me what is the convergence of this function? Where does this fn converge? You can see that fn converges to f as n goes to infinity, and we'll always write pointwise or uniform, depends upon the condition. So what is that f? Apply n goes to infinity here. 0. It means it is 1 when x is greater than or equal to 0. And it is minus 1n when x is less than 0. The problem is this thing vanishes. Because when you apply n goes to infinity, what happens? This becomes 0 and this becomes 0. So exactly at this point 0, your function is x. Okay. And if you put 0 in x, that becomes 0. It means that point is emerged into a pointwise discontinuity. So this is not that much interesting. This is not interesting because this thing vanishes if you apply n goes to infinity. So this is the limit of this sequence of functions fn. What is the graph of this one? You will see it is going to be 1 from here and it is going to be minus 1 from here. So this is the graph of f and this is the graph of fn. And you can see that this line goes nearer and nearer to this point, and this line goes nearer and nearer to this point. Eventually you will reach at this situation. What is the problem here? When you have some sequence of fn, can you tell me that fn is continuous for each n? You took f1, is f1 continuous? You can see the graph. It is continuous. Is f2 continuous? You can see it comes like this, goes down, it goes like this, it is continuous. So f1, f2, f3, these all are continuous, but their limit is not continuous. The limit is not continuous. We say that fn converges to f pointwise if their limit is not continuous, but the functions itself for all n are continuous. This is what we call the pointwise convergence. So if fn is discontinuous, fn is continuous but f is discontinuous, we call they converge pointwise but not uniform. But when fn continuous for all n and f is also continuous on that interval, we are not going outside the interval, then we say that okay, this is uniform convergence. Uniform convergence.
इनके भी ग्राफ में कांटे का होल चल था
Yes.
तो वो पॉइंट वाइज हो जाएगी इन छोड़ा था फंक्शन से कंटीन्यूअस है नजर चलो
fn is continuous.
हां वो जारी है
fn is continuous.
ऐसे जो होनी जरूरी है वो ना हो तो कहीं की
No, it's not necessary.
अच्छा
It's not necessary. But you see, fn is continuous, but f is not continuous. That's the pointwise convergence. But if fn is continuous, implies f is continuous.
यूनिफॉर्म
That is uniform convergence. Now I'm writing the definition of uniform convergence. So Fn converges to F uniformly as n goes to infinity if and only if what happens. It means what is going to be the definition. Definition is same. Fn evaluated x minus f of x should be made as small as possible. But when? The definition looks like the same as we discussed earlier, but there is a problem in this one. For all epsilon, there exists n and n. For all x in your interval I, this thing happens whenever you go beyond that. What is the difference between that definition and this definition? We wrote the definition of pointwise convergence. Now I have written the definition of uniform convergence. Can you tell me what is the difference? I have written already the definition of, I think, pointwise.
For all epsilon can declare like for all x by
Yes, that's the difference. For all x means you choose any x first. Then you see, okay, what happens. You choose x means you are fixing your x. Here what you do, you choose your epsilon. Then for this, you choose any epsilon. Then this epsilon must work for all x. First of all, what we are doing, we are choosing a particular x. Then we are choosing, okay, what happens. Here what we are doing, we are saying, okay, this is the epsilon. Now this epsilon must work for all x, whatever you take. If you change the order of these quantifiers, then the situation becomes different. And we say this is the definition of uniform convergence.
What's the difference? Is it only को fix ही थियो ना? Choose the x ही करना.
Yes.
Epsilon जो कोई तो वो हर दफे को fix ही थियो ना?
You choose different x, the epsilon can be different. You choose x something else, epsilon is going to be something else. But here you are choosing a fixed epsilon, then this epsilon must work for all x. If it does not work for some chosen x, we say that okay, this is not uniform convergence.
और throughout हिपी limit होगी
Yes,
ग्राफ
yes,
इस limit होगा.
Yes. What happens basically in uniform convergence, you have a function f to which a sequence converges. Then you make some epsilon ball around this. And let me tell you, this is also called epsilon ball. It is not interval, it is not disk, it is not a sphere, it is epsilon ball. It is epsilon ball. Because towards this function you go somehow epsilon down and epsilon up. We call this is the epsilon ball around f. Then your all fn lie in this epsilon ball. Whatever fn you take, they must lie in this one. Whenever n goes to infinity, whenever n becomes large. So this is what we call the epsilon ball around f, and each fn lies in this epsilon ball. And if I say you, okay, what is the epsilon ball around sine t? Can you tell me what is that? How to make epsilon ball around sine t? So you make a graph of sine t that I think looks like this, and you make some epsilon ball around this. It's somehow looking like this. And we can also discuss, okay, what is the value of for this particular thing and for this particular thing. We can discuss that thing as well. I think that would be sine t minus epsilon and sine t plus epsilon for all t, whatever they are. So this is the epsilon bar around sine t. Okay, so one last remark about this one, that uniform convergence implies pointwise convergence.
But pointwise convergence are true.
Yes, pointwise convergence may or may not imply uniform convergence. This is the main thing that should be kept in mind. So we are not supposed to check this definition every time. Okay, what happens? Just Fn is given to you, check what is the limit. If Fn is continuous, the limit is continuous, that's a uniform. But if the limit is not continuous, there is a pointwise. Okay, so
For example, in your theory,
yes,
cover
I am doing the same thing. So let me write example. You may think for it for now. So this is n square x and n square x square plus 1. Just tell me one thing, that is it continuous for all n? Whatever n you take, is it continuous?
Yes.
You take n is equal to 1. What is f1? X over x square plus 1. Is it continuous? Everywhere. What is the point of discontinuity? You said x square plus 1 equals to 0. That becomes, I think, plus minus iota. Plus minus iota does not belong to the set of real numbers, so there is no discontinuity. There is no discontinuity. What is f2? That is 4x over 4x square plus 1. Continuous? So it is continuous everywhere. What happens if you apply limit n goes to infinity?
X upon x square plus 0. 1 upon x is
This is on minus infinity to plus infinity. You have to see this thing. So what is f of x? The limit of this one?
1 upon x.
1 upon x?
1 upon x is
Yes, it would be 1 upon x. Is it continuous on this one?
0 to 0.
Not on 0. It means this sequence is continuous for all n, but the limit is not continuous on some fixed value in this interval. Then we say that this converges to this pointwise, but not uniform.
But interval we see is not Japan.
Yes. But if the interval is something else, let's say from 1 to positive infinity, then this converges to this uniform. You have to see the interval as well. And what is the problem in the interval? That thing must be seen. Can you draw the graph of this function? This is very easy. I think it looks like this. It looks like this. Exactly, there is a problem at 0. But if you put 1 here, you get this graph. And this graph somehow looks like this. It goes near to 0, then it goes somehow up, then comes down, and then it goes in this way. If you take f2, it will be doing something like this. It will go somehow up, then comes down, then converges to this one as well. So f1, f2, these all are continuous. f1, f2, f3, these all are continuous in this way, but exactly their limit 1 over x is not continuous at x is equal to 0. So you can graph these easily with the help of Desmos. So this is what we call the pointwise and uniform convergence.